Suppose that we have a Towers of Hanoi problem of size n, by which we mean that there are n disks that have to be moved from one pole to another. In this example, n is 5. What should we do?
Our problem is to move these 5 disks over to this pole consistent with the rules of Towers of Hanoi. Recall that the rules say I can only move one disk at a time. I can never just leave a disk off of a pole, and I can never put a smaller disk underneath a larger disk. All right? So how are we going to solve this problem? We're going to divide it into some subproblems. First thing to recognize is at some point, this red disk must move from this pole, pole number 1, to this pole, pole number 3. That must happen. Now, what does the configuration look like when that has moved? Well, in order to move disk 5 from this pole to this pole, all of the other disks must be on pole 2. Now look at that. That looks like sort of a 4-disk situation. Furthermore, to complete the solution for the 5-disk problem, we need to put these 4 disks over on pole 3. And again, that's a 4-disk problem. To say that again, to solve the 5-disk problem, we solve first a 4-disk problem, move the 5th disk, and then solve another 4-disk problem. All right, then let's concentrate for a moment on simply a 4-disk problem. Again, at some point, the bottom disk, in this case the orange disk, must move to a different pole. All right, the other disks must be out of the way to do that. Then I move the bottom disk to pole 2, and then I move the others back on top of the orange disk, and that solves the 4-disk problem. Again, to solve the 4-disk problem, I solve a 3-disk problem, I move the bottom disk, and then I solve another 3-disk problem. So now we see to solve the original problem, we needed to solve 2 4-disk subproblems, and now to solve a 4-disk subproblem, we see we need to solve 2 3-disk subproblems, or if you like, sub-subproblems. All right, so now we're looking at solving a 3-disk problem. Okay, again, we must move the bottom disk at some point. All right, for us to do that, we must have the other disks out of the way. And you see, to do that, we need to solve a 2-disk problem. And of course, we do a 2-disk problem, we move the bottom disk, then we do another 2-disk problem. We have now reduced the original problem to a 2-disk problem, and of course, again, we could reduce that to a 1-disk problem, move one disk, move another disk, move the 3rd disk, and that's all that happens. Now, let's try to talk about the amount of work that is required to solve these problems. We have said to solve the 5-disk problem, we need to solve 2 4-disk problems. But to solve the 4-disk problems, we need to solve 2 3-disk problems. Well, that means to solve the larger problem, there's going to be 4 3-disk problems. Of course, to solve those 4 3-disk problems, for each one of them, there has to be 2 2-disk problems. So now we're 8 2-disk problems, and we could subdivide that further, that there are 16 1-disk problems to solve. Now let's look in general. This is a 5-disk situation, but suppose there was some other number here, a large number, and let's just call that n. So let's pretend that this red disk is the nth disk, and these are n-1 disks here. How many moves must we take? Well, first we must solve an n-1 disk problem. Then we have one extra move to move the bottom disk, and then we solve another n-1 disk problem. So what we have shown is to solve an n-disk problem, we must solve two n-1 disk problems plus one extra move. Once again, the number of moves for an n-disk problem is equal to twice the work, the number of moves for an n-1 disk problem plus one move. And that holds for every value of n.
The solution you've just seen is an example of a recursive algorithm. A recursive algorithm solves a larger problem by invoking itself on a smaller problem. In this case, we have to move the top 4 disks out of the way. That invocation can do the same thing. In this case, get the top 3 out of the way. This process continues until it needs to solve some very small, we can think of it as a base case problem. We solve that problem. In this case, we need to move the bottom red disk to pole 3. And then we solve a second smaller problem. We move the 4 disks back from pole 2 to pole 3. Recursive algorithms play a very important role in computing. As in this example, they're often simple and easy to reason about. For example, we know how many moves are required to move n disks. Moving 1 disk takes exactly 1 move. To move 2 disks, we must move the smaller one, then the bigger one, then the smaller one again. So a total of 3. To move 3 disks, we have to move 2, then the big one, then 2 again. So 7. To move 4 disks, we must move 3 twice, with the biggest one in between, and so forth. Suppose that we want to move n disks. Call the number of moves required to move n-1 disks m of n-1. Then we can describe the number of moves for n disks in terms of that. We move n-1 disks twice, plus the 1 move for the biggest disk. You can call this m of n. Look at this chart. What we see, apparently, is that to move n disks requires 2 to the n minus 1 moves. We observe that here. We haven't proved it, but it turns out to be possible to prove that that's correct using a technique called mathematical induction. Let's return to our original legend. For the 64 disks our story started with, that means 2 to the 64 minus 1 moves. So even if there were a legend, and it were true that the fate of the world depended on the monks in Hanoi, we wouldn't actually have too much to worry about. 2 to the n grows very fast. At 1 move per second, to move 64 disks would take over 584 billion years. Yet, there have been only about 13.8 billion years since the Big Bang. A long ways to go. Computers have no difficulty executing recursive algorithms because they can maintain a stack of tasks that they must come back to. For example, to solve a Towers of Hanoi problem takes 3 steps. Each entry in the stack corresponds to one of the subtasks, with the one that needs to be done first on the top. For a problem of size n, it's necessary first to move the top n-1 disks. So we'll pop the top. Notice that while we were focusing on that subtask, the stack remembered that we still had 2 more tasks to do. And next, we again pop the top element off the stack and perform its job, which is to move the bottom disk. Finally, we pop the final element off the stack and do its job, namely moving the top n-1 disks again. Now the stack is empty, indicating no more subtasks, at the same time that the complete task is finished. Unfortunately, people aren't very good at managing stacks with more than a few items. So the solution you just watched didn't actually use the recursive algorithm that we've just described. It turns out that for this problem, though, there's a non-recursive algorithm as well, often called an iterative one, that leads to exactly the same sequence of moves. Let's look at it. Assume that the goal is to move the stack of disks from pole 1 to pole 3. Think of the poles as being arranged in a circle. On odd-numbered moves, starting with the first, we move the smallest disk. which direction. If the original number of disks was even, move it clockwise. If the original number of disks was odd, move it counterclockwise. We have an odd number of disks in this case, so we move yellow counterclockwise. On even numbered moves, make the only other move that's legal and doesn't undo the previous move. So we move green to pole 2. Now yellow counterclockwise again, and so forth. Now let's watch our solution again. You can see that this is exactly what's happening. So our iterative solution works, but compared to the recursive one, we would have a much harder time understanding why it works or analyzing it to see how many moves it takes. So we've seen the power of recursive algorithms.